Now, I do want to bring your attention to the relationship between momentum and kinetic energy. Uh, Kinetic energy uh, also describes motion, just as momentum describes motion. Both of them have equations that have the velocity variable in them. In momentum, we have this equation, which is mass times velocity. In kinetic energy, the equation is 1/2 mv squared, or as I like to put it, mv squared divided by 2. Keep in mind that there is a relationship between momentum and kinetic energy. Any object that moves has momentum and as well has kinetic energy. Now, how do they relate to each other? Well, you'll notice that kinetic energy is the result of an object's momentum to the power of 2. What do I mean by that? Well, let's go ahead and do some substitutions here. We're actually going to take this momentum equation and combine it to the kinetic energy equation. So let me give you an example of that really quick. Okay, here are our equations for momentum and kinetic energy. Now, how can we show that both of them are related? Well, the question we should ask is, what's the common variable that each of these equations share? Velocity. Both momentum and kinetic energy have the velocity variable in their equations. So what I'm going to do is I'm going to take this momentum equation and rearrange it to solve for velocity. Well, if we're trying to solve for velocity using the momentum equation, well, we definitely have to divide mass on both sides. So that way it cancels out, and our equation for velocity using the momentum equation is momentum divided by mass. So we can look at it this way. To find an object's velocity, we can take the object's momentum and divide it by the object's mass. Now, since velocity also shows up on the kinetic energy equation, why don't we substitute that velocity for what it stands for in the momentum equation? In other words, what I mean by is this. Okay, so what you see here is a substitution of velocity with the momentum equation that was rearranged. So in other words, I took this velocity here and I just replaced that velocity with that equation. Since momentum divided by mass equals velocity, I just substituted it for it in here, just like that. And now we get this in our kinetic energy equation. Well, you'll notice that after you have set this up just like that, let me break it down even further so you can kind of see what's going on. Okay, so this is how it looks like after it was broken down. I just, basically wrote it like this. You'll notice that one of the masses cancels out with one of the other masses. And now you have an equation that looks like this. Kinetic energy equals momentum squared divided by 2 times the object's mass. And so when you look at this, you'll notice that momentum and kinetic energy are proportional to each other. If the kinetic energy increases, so does the object's momentum squared. Now you'll notice that any factorial change, any factor change to the momentum significantly increases kinetic energy to the power of 2. In other words, what I'm trying to say is, what happens if I double an object's momentum? Well, if I double the object's momentum, the kinetic energy increases by a factor of 4. What happens if I triple my momentum? Well, if I triple my momentum, my kinetic energy significantly increases by 9 times. And so basically what you need to know in regards to the relationship between momentum and kinetic energy, both of them are proportional to each other to a power. It's basically proportional to the power. So note that any increase in the momentum will significantly increase on the kinetic energy and vice versa.